Have you ever wondered how complex artificial intelligence systems make decisions, recognize faces, or even understand language? At the heart of these incredible capabilities lies a surprisingly simple yet powerful component. A neuron in a neural network is the fundamental processing unit, conceptually inspired by the biological neurons in our brains. It takes one or more input values, processes them, and then produces an output value. Think of it as a tiny decision maker within a vast interconnected system. The core mechanism of a neuron involves several steps. Each input it receives is first multiplied by a corresponding weight. These weights representing the strength or importance of each input connection. All these weighted inputs are then summed together, and a bias value is added to this sum. Finally, this total sum passes through an activation function, which determines the neuron's final output, often introducing nonlinearity to the model. The weights and biases are the learnable parameters that allow the network to adapt and improve its performance over time. Practically, these individual neurons are organized into layers. The output of one neuron can serve as an input to many other neurons in subsequent layers, allowing information to flow and transform throughout the network. This structured flow enables the network to detect patterns, make classifications, or generate predictions by combining the simple processing power of many individual neurons. Historically, the simplest form of an artificial neuron was known as a perceptron, developed in the 1950s. The inclusion of activation functions is critical because it allows neural networks to model nonlinear relationships in data, which is essential for solving complex real-world problems that cannot be understood with simple linear equations. Without these nonlinearities, a deep neural network would simply be equivalent to a single-layer linear model, severely limiting its learning capacity. Understanding the role and function of a single neuron is key to demystifying how neural networks learn and perform intricate tasks. It illustrates how sophisticated intelligence emerges from the coordinated activity of many basic computational units, continuously adjusting their internal parameters to better understand and interact with the world around them.